Hi there, I'm Dr. McFerrin. In this video, I'm going to talk about the steady state response of a system. So before I get into the steady state response, let me first make sure that I remind you of some important definitions. The first is that the initial value of a system is f of 0. I'll say 0 plus. This is the time immediately after 0. This is equal to the limit as s approaches infinity of s f of s. So this is the value before any time has passed once the system turns on. The final value is the value of the system response after all time has passed. So this is f at infinity, or at least as time approaches infinity. And this is equal to the limit as s approaches 0 of s f of s. Sometimes this is referred to as the DC gain. So let's dive into the primary definition for today, which is the steady state error. The steady state error, ESS, is equal to E of infinity. So using the final value theorem, this is the limit as s approaches 0 of s E of s, which is just the final value theorem I just wrote. Now, let's recall the following form for a system. R of s, sum into here, gives me E of s. E is the error, and I'm going to say G of s. Here's my output Y of s, and then here is the feedback loop. So the error E of s is just equal to R of s minus Y of s. But I also know that Y of s is equal to G of s times E of s, thanks to the way that signals move through systems in block diagrams. So if I plug that in, that means that E of s is equal to R of s minus G of s E of s. Or in other words, E as a function of s is R of s over 1 plus G of s. So then the steady state error is equal to the limit as s approaches 0 of s times R of s over 1 plus G of s. This is my principal equation that I'm going to use. Now, there are a bunch of different sources in a system of steady state error. There may be error that comes from nonlinearities, some error from the way the system is configured. It may also be due just to the type of the applied input. And so let's look at different test inputs to a system. Delta of t, the unit impulse, Laplace transforms to 1. If I draw that in the time domain, it just has a value of 1 at t equal to 0. U of t is the unit step, which transforms to 1 over s, which has a value of 1 as long as t is greater than or equal to 0. This is what's called the unit step. The first one is the impulse. Next I have t, U of t. This is what's called a ramp. It transforms to 1 over s squared. So this is a ramp. And the way that that's going to look is that it turns on at t equal to 0, and it increases linearly with time. And then the last form is t squared over 2 u of t, which transforms to 1 over s cubed. And this is a system who, in the time domain, looks parabolic. So this is t squared over 2. This is a parabola. If a system is a step input, let's refer back to ESS. ESS is equal to the limit as s approaches 0 of s R of s over 1 plus G of s. If I have the unit step, which is 1 over s, what happens is that the s up here is going to cancel. And so I'm plugging that in for R of s. Let's So let's review. ESS is equal to the limit as s approaches 0 of s times r of s over 1 plus g of s. So if I put in 1 over s in for r of s, then this is going to equal to the limit as s approaches 0 of 1 over 1 plus g of s. If I take this limit, the only place that it matters is in this g of s, so this is equal to 1 over 1 plus the limit as s approaches 0 of g of s. On the other hand, for a ramp input, reminder, ESS is equal to the limit as s approaches 0 of s times now 1 over s squared, 1 plus g of s. So as s approaches 0, I'm going to cancel an s with an s squared. So I get 1 over s plus s g of s. And I'm taking the limit as s approaches 0. So that's equal to 1 over the limit as s approaches 0 of s g of s. So I now have steady state for a step and steady state for a ramp. Let's look at one more for a parabolic. Using the same procedure, I'll find that ESS parabolic is equal to 1 over the limit as s approaches 0 of s squared g of s. Now, what I notice is that each of these have specific denominator terms, and these terms are called the static error constants. Let's refer to Kp as the limit as s approaches 0 of g of s, and this is what's called the position error constant. We also have Kv, which is equal to the limit as s approaches 0 of s g of s. This is called the velocity error constant. And then we have Ka, which is the limit as s approaches 0 of s squared g of s, which is called the acceleration error constant. And that's because I'm taking g of s, and in the first place I'm assuming its position, then I take the derivative of it, which is velocity, then I take the derivative of that, which is acceleration. Now, before I talk about how a system behaves, I need to define what's called the system type. So the input to the system, r of s, is here. And then I've got my summer, and then I've got E of s, and then I've got a system, which we'll say is K over S plus Z1, S plus Z2, these stand in for zeros, over S to the power N, S plus P1, S plus P2, and so on. And then I've got Y of s, and then I'm going to have unity feedback, which means that I just have a wire feeding back from Y to that error. Now, what I'm going to do is I'm going to say that the system type, and this is very important, so I want to make sure that you catch this. The system type is the value in of pure integrators. So in other words, if I have a system which looks like S plus 1 over S, S plus 2, S plus 3, there is exactly 1, n equals to 1, and so I call this type 1. If this higher power of n is 0, then I call it type 0, and if n equals 2, then it's type 2. So I want to be really careful that I make sure I get this. When I factor out all of my poles, the number of poles located at 0, that's the number of pure integrators in the system, that is the system type. So that's where that comes from. Now that I have that type, what I'm going to do is I'm going to form one big table where, based on input, we can figure out for what type, or what the value is based on type. So type 0, type 1, and type 2. So I'm going to write the constant and the error for each. So let's start with a unit step, U of t. The steady state error formula for a unit step is 1 over 1 plus Kp. I've already derived that above, but I want to make sure that I formalize it here. For a ramp, which is t u of t, I use 1 over kv. And for a parabola, or parabolic, I've got t squared over 2 u of t. I'm going to use 1 over ka. So for step, I use the position constant. For ramp, I use the velocity constant. And for parabolic, I use the acceleration constant. Then, let's look by system type. Let's look at a step input for a system of type 0. In this case, Kp is equal to a constant. Kp is a constant. The reason for that, let me give you a little detail. So let's say I've got 1 over s plus 1. This is a type 0 system because I can't pull any s's out front. And if I take the limit as s approaches 0 of this, it's equal to 1 over 1. That's what happens when s becomes 0. That's just a constant value. The error in this case is in fact 1 over 1 plus kp, that constant I just calculated. For a type 1 system, the constant here, kp, let's look at that. That's the limit as s approaches 0, but I've got a type 1, so I'm going to say s over s plus 1 as s approaches 0. What happens is I get 1 over 0, which goes towards infinity. So in this case, for a type 1 system, kp is trending towards infinity. And if I put that into my equation, 1 over 1 plus kp, if I put that into my equation, 1 over 1 plus kp, that's equal to 0. For a type 2 system, same story. So if I have the limit as s approaches 0 of 1 over s squared s plus 1, this goes towards infinity as s approaches 0. So I've got infinity and 0. For a ramp input for a type 0 system, I'm going to have 1 over the limit as s approaches 0 of s times my system. If it's a type 0 system and I add an s in there, what I find is that kv equals to 0, which means my steady state error is infinity. For a type 1 system, let's sort of go back here. For a type 1 system, I've got s, g of s. For a type 1 system, my s's will cancel each other, and so kv is a constant. And so I've got 1 over kv. And for a type 2 system, kv is equal to infinity, and there's 0 steady state error. Finally, for a parabolic system, I'm looking at ka. Ka is equal to 0 for a type 0 system because I'm going to get s squared times my g of s, and a type 0 system has no s's in the denominator to cancel that, so that gives me infinity. Same thing for type 1. Ka equals 0 and infinity. And in this case, Ka for type 2 is a constant, and I get 1 over Ka is the value. All right, now let's interpret these results a little bit. As I look through this, I'll see that for type 0, I'm going to get an actual number value for steady state error. If I have a type 1 or type 2 system, I'll get 0 steady state error. In other words, it will track the unit step perfectly. For a ramp, what happens is that for type 0 system, kv equals to 0, which means that the error is infinity, or in other words, the system does not track the ramp at all. For a type 1 system, I get a value, and for a type 2 system, I get 0 steady state error. For a parabolic input, type 0 and 1 do not track, and for a type 2 system, I have a chance of tracking with a numerical value error. All right, let's put this all together in one example. Example 1, let's say I'm given g of s, which is equal to 1,000 s plus 8 over s plus 7, s plus 9. And I want to find the system type, and then I want to find Kp, Kv, Ka, and then I want to find the steady state error for the different test inputs. So find the steady state error for a step, a ramp, and a parabola. or parabolic input. So first thing is to look at the system and find the system type. If I take this system, what I notice is that g of s has no pure integrators. There's no 1 over s's that can be pulled out. So this makes it a type 0 system. Since I have the type, the next thing I want to do is find Kp. Kp is equal to the limit as s approaches 0 of g of s, which is just equal to 1,000 times 8 over 7 times 9, which when I calculate that out is roughly 127. Then I can find Kv. Kv is the limit as s approaches 0 of s g of s, and this is equal to 0 because there's no s's to cancel that. Same thing with Ka. Then I want to find ESS, so let's start with the step. For a step, it's 1 over 1 plus Kp, so that's 1 over 1 plus 127, or in other words, 1 over 128, which is 0.0078. Relatively small. In other words, what this is doing is, as I have a step input, so let's say the actual value is this dashed line, the step input is going to get close but not be exactly right. It'll be off by 0.0078. For ESS for a ramp, I've got 1 over Kv, which is 1 over 0, which trends towards infinity, and ESS for a parabolic is 1 over Ka, which is 1 over 0, which trends towards infinity. Now I've got my answers. So in summary, what we did is we talked about steady state error, which is the difference between the actual output and the desired response. And so what I'm trying to do over time is I'm going to try to develop control systems which allow me to drive this steady state error closer to 0, so that way my output gets closer to my desired or reference input. That's all for now. Thanks for watching.